Okay, so welcome back everyone for our next speaker, who is Eugene Rabinovich from the University of California, Berkeley, but is moving now to the University of Notre Dame. He's talking about factorization algebras for bulk boundary systems. Please.
Okay, thank you for that introduction, Nima, and thanks to the organizers for the invitation. I'm really enjoying this conference. I think it's really well organized, and I've enjoyed the talks. And I apologize to the morning speakers because I am not able to attend your talks on account of being asleep. But anyway, I'm excited to be here, and I would also like to say that I am not used to speaking into a void for 50 minutes, so I would be happy if you interrupt me with questions. Okay, so yes, like Nima said, I'm going to be talking about factorization algebras for bulk boundary systems. So first I'll give a bit of a very high level summary of what the talk is about. So we saw this a bit in Nicola's talk, sorry. A factorization algebra on a manifold, it's a Cauchy-like object, and it's supposed to encode the structure present in the classical or quantum observables of a perturbative quantum field theory. This might be the only time I say the word perturbative, but it should be sprinkled throughout. So just from the beginning, everything's going to be perturbative. So Kevin Costello and Owen William have shown precisely that in any classical and or quantum field theory on a manifold M, that's the space-time, gives you a factorization algebra of observables. So in their situation, this M is closed. Not closed, but there's no boundary here. So in my dissertation, which I just finished, I extend the techniques of Owen and Kevin to situations where the manifold is not empty. And part of that dissertation is joint work with Owen William and Brian Williams. But anyway, so apart from being interesting to people who are already interested in bulk boundary situations, the techniques can be understood as part of a program to study what might be called Poisson BV theories. That is, BV field theories that are described by shifted Poisson geometry as opposed to shifted symplectic geometry. So in this talk, I'm going to survey the techniques that I talked about here, and we're going to show what happens when you apply them to two simple examples. Topological mechanics and BF theory in one dimension. And these are both theories in one dimension, but so not necessarily the most exciting quantum field theoretical theories, but they illustrate some interesting phenomena. So yeah, we'll see. Essentially what we'll see is that for the quantizations of these theories using my techniques coincides with what you would expect from Ansätze that are particular to these theories. So as a quick outline, so we just did the introduction, then I'm going to talk about some background on factorization algebras and classical bulk boundary systems. Then I'm going to give a very quick overview of how to quantize bulk boundary systems. And then finally, we'll discuss the basic examples that I just talked about. So we saw this in Nicola's talk, but I'm a believer that it never hurts to repeat things. So a factorization algebra, it's a sort of object that's something between algebra and geometry in the way that vertex algebras are and the way that EN algebras are. So if we have a topological space, factorization algebra consists of the data of a cochain complex for every open subset of that topological space, and for every pairwise disjoint collection of open sets, including into another larger open set, we have this structure map, which goes from the tensor product of these cochain complexes into the bigger set. I'll draw a picture of this in a second. You might be familiar with some special cases of factorization algebras. So factorization algebras, which are so-called locally constant on Rn, give rise to EN algebras. And factorization algebras, which have a certain sort of holomorphic nature on C, give rise to vertex algebras. So here's a quick picture. So for every open subset U, we will obtain some cochain complex F of U. And then whenever we have some large open subset with some smaller open subsets in it, we will get a map from the tensor product here to the bigger space. So we'll get a map like this. And there are some extra conditions that are involved in this definition. One natural condition you might hope to write down is some sort of associativity condition. So for example, if we include these two smaller opens into a larger open, there's the factorization product there. And then we can include this open and this open into V and get another factorization product. Or we could compose, or we could just go straight, or we could just compute this map here. So let me, so let's say this is W. So we also have F of W tensor F of U3. And we have structure maps going this way and a structure map going this way. And one of the conditions of a factorization algebra is that all such diagrams commute. It's a natural associativity condition in similar to the associativity for associative algebras. So now let me present to you a very simple example of a factorization algebra on the non-negative real line, which is basically the crucial example that all our results relate to. So it's a good moment to make sure you're paying attention and ask questions. So the data for this factorization algebra is going to be an associative algebra and a right-pointed A module. And we'll describe a factorization algebra on the real line. Which is going to assign, let me draw it this way. So to any open subset containing the boundary point, it's going to assign M. And to any open subset, sorry, not any connected open subset not containing the boundary point, it's going to assign A, the algebra. So this is also M here. And that's A. And the structure maps are going to look like, so the structure map for, say, M A into a bigger guy that contains the boundary, structure map for this inclusion, well, that should be a map from M tensor A to M. Well, that's just, this is just the A module structure on M. And similarly, when we just include two open intervals into a larger open interval, which also corresponds to the algebra, we get a map from A tensor A to A, and that's just the multiplication in A. Okay, so this is the sort of archetype, since we're considering theories on the non-negative reals, this is the archetype of the sorts of factorization algebras we would like to obtain as observables for these theories. All right. Okay, so now we'll describe what a bulk boundary system is, since we're supposed to obtain a factorization algebra from a bulk boundary system. So if you have a manifold with a boundary, bulk boundary system is a pretty simple object for those that, you know, whose bread and butter is BV-BFV. First, I have a BV-BFV theory. So in particular, this is a zero-shifted symplectic space of fields, of boundary fields. And this is, let's say, wants to be a -1 shifted symplectic space. This boundary, there's data on the boundary that measures the failure of this object to be -1 shifted symplectic. So we take that data and we also choose a Lagrangian in the boundary zero shifted symplectic space. So I'll explain in a moment why what the geometric meaning of this is. But first, let me just say that one of the theorems of my dissertation, it's actually posted on the archive right now, this particular result, that any classical bulk boundary system on M determines a P0 factorization algebra of classical observables. So this means that f of u is a DG commutative algebra with a Poisson bracket of degree +1 for all open subsets here. That's what I mean by P0 factorization algebra. And this is the sort of thing you would expect as like the functions on a -1 shifted symplectic stack will be a P0 algebra. So let me make some notes. So first, I consider particular types of bulk boundary systems a lot of extra conditions, but you can still study a fair number of theories even with the conditions that I impose. And then I want to explain a bit more about this, the data here. So part of the data of a BV-BFV theory is this map from the bulk fields to the boundary fields, which basically takes boundary values. And in fact, you can show, at least for the types of theories I consider, that this is a Lagrangian. This map has a Lagrangian structure. So the bulk fields are not necessarily -1 shifted symplectic, but they embed as a Lagrangian in the boundary fields. And so the choice of this extra Lagrangian here serves to provide another Lagrangian so that we could take the homotopy pullback and we will expect that the homotopy pullback is -1 shifted symplectic, as it's the derived intersection of two Lagrangians in a 0 shifted symplectic space.
So may I ask a question?
Certainly.
So you were talking about that this map is Lagrangian. Can you just say a couple of words on the map, like?
Yes.
Yeah.
What about why it's Lagrangian, or about what the map is, or?
Both maybe, like, yeah.
Yes, I'll just say a couple of words. So I won't say why it's Lagrangian, but I will say why it's coisotropic. So in my language, there's a, so let's call this map rho. So what we find is that the pullback, so recall that I said that this wants to be -1 shifted symplectic. So there's the pairing of degree -1, which would be the -1 shifted symplectic structure. So what we find is that the pullback of the symplectic form on the boundary fields is not 0, but it's it's the differential of this operator, of this pairing. So this pairing, which doesn't give a -1 shifted symplectic structure for when you have on the bulk fields, when you have a boundary, it at least tells us that that it at least provides a homotopical trivialization of the pullback of the symplectic form on the boundary fields to the bulk fields. So that's a statement of the the isotropy of the bulk fields in the boundary fields. And then you have to do some sort of, you have to be a bit more, I mean, these are infinite dimensional spaces, so the Lagrangian condition is a bit more technical.
Yes, exactly. So I'm okay. There's another short question from Pele, I guess.
Yeah.
Thank you. So would it be fair to say that your theorem is a consequence of the Lagrangian, the statement that you just mentioned, that this projection P is has a Lagrangian structure, because it's a general fact that if you have a Lagrangian inside something zero shifted symplectic, then on the source of the Lagrangian morphism, there is a -1 shifted Poisson structure. Is that a fair assessment of your theorem?
Yes, except that there's also infinite dimensional stuff that,
okay, yeah,
and like Cauchy, like Weiss codescent type things that need to be verified. So, morally, yes, exactly. Morally, the classical observables are just the functions on this homotopy pullback.
yeah.
So, like you said, you do expect this to be P0. But again, because of infinite dimensionality of
you have to, doesn't follow from some, general theorem.
Yeah.
In derived algebraic geometry, you have to prove this in your setting.
Yes.
By hand. Okay, thank you. That was my question.
Okay, any more questions? All right. All right, so this is a very rough outline of what a bulk boundary system, classical bulk boundary system is. Now I'm going to explain a source of bulk boundary systems, which are the so-called Poisson BV theories. So if you want to zone out for this slide, let me just say that Poisson BV theories are a source of bulk boundary systems. So now we actually are going to back to manifolds without boundary. So you might think of this as the boundary, e.g. n is the boundary of some manifold. In the ordinary BV formalism, field theories are described by -1 shifted symplectic spaces, like we've seen. Poisson BV theories are described by shifted Poisson geometry instead of shifted symplectic geometry. So one important thing to note is that a Poisson BV theory gives rise to a bulk boundary system on a manifold with boundary in one higher dimension, which is the so-called universal bulk boundary system for T. And conversely, if you have a bulk boundary system, the boundary condition inherits a Poisson BV theory structure on the boundary. And none of this is my work. I would say this is work of Butson and Yu. And there are probably antecedents for that work as well, which I'm unfortunately unaware of. At the very least, Kontsevich sort of knew this in his heart of hearts when he quantized Poisson manifolds. Let me just make sure I don't want to say anything else. Yes, so I will comment that, like I said, Kontsevich knew this in his heart of hearts. So he wanted to quantize a Poisson algebra of functions on a manifold, which is you can encode as a Poisson BV theory on R. And what he did was he passed to this bulk boundary system on the upper half space. And he quantized this bulk boundary system and saw that that induced a quantization of the Poisson BV theory on the boundary. So I'll talk about this a little bit more later.
So here, maybe I can just add, like here, I mean, Kontsevich also already knew probably about the Poisson sigma model. That's also something that is, which you can use as a BV theory in this setting, right?
Yeah, exactly. So the Poisson sigma model is the corresponding universal bulk boundary system for this Poisson topological mechanics. Yeah, exactly. So, right. All right, so let me run through some examples very quickly. A lot of them will come back again. So topological mechanics has as its space, so we choose first some symplectic vector space. V and some Lagrangian subspace, linear subspace. And we can form a BV theory on the non-negative reals whose fields are the de Rham complex with values in V. The boundary fields are just V because the boundary is a point, and as our Lagrangian, we just choose a Lagrangian subspace of V. Pretty simple theory. You can also do Abelian-Chern-Simons with chiral WZW boundary condition. And here M is an I'll put it here. So M is an oriented 3 manifold. The space of bulk fields is shifted de Rham complex here. Space of boundary fields is this shifted de Rham complex on the boundary. And for a Lagrangian, we choose a complex structure on the 2 manifold on the boundary, and we just take the 1 star forms on the boundary. Great. I won't talk about this example, but this is the central example of my paper with Brian and Owen.
Can I ask something stupid maybe, so
Sure.
do you usually want in topological mechanics to be compact? Like, do you want to have S1 or just positive?
I prefer to work on flat spaces. So I like to do it on, say, the positive. I don't need compactness.
Okay.
And so this sort of, like we saw, there's a nice factorization algebra on the non-negative real line for any algebra and module. And I put it this way so that I can compare the factorization algebras of observance. So BF theory is very similar. It's also topological. So space of fields is de Rham forms on M with values in G shifted down and G dual shift, and same thing for the boundary fields. In BF theory, you have 2 boundary conditions. You can either choose this component or this component, this component or this component for the boundary fields. And I just want to say that on manifolds of the form n M equals n cross all these examples except this, the one with this boundary condition here. All of the examples are the universal bulk boundary systems for Poisson BV theories. So these are also examples of Poisson BV theories implicitly, but I won't explain that in too much more detail. So now let's talk about quantum bulk boundary systems. So I wish I could explain how to define such an object, but it's a lot of work. So I can do it, I just don't think anybody would. I don't think it would be very enlightening. But the definition is along the lines of Costello's. So essentially what I have is a family of interactions, one for each length, heat kernel scale, and they're related by homotopical RG flow. Each of the interactions satisfies a version of the quantum master equation, and you have a certain asymptotic locality condition on these interactions. So that's all I'll say about that. So this definition is very similar. The main new ingredients is a careful study of how to construct the appropriate propagators for bulk boundary systems, and a characterization of how to describe local functionals on manifolds with boundary. So I think those are the main things that are new, besides careful checking of that everything that worked when there was no boundary works still when there is a boundary.
So maybe I can ask another question. So the sort of thing is that the difference of the BV-BFE formalism to the way that you are basically constructing the things, right, is that you're choosing boundary conditions.
Yes.
Right, instead of having like a polarization for the quantization, right?
Yes.
So you still stick to the usual like classical and quantum master equations instead of having these modified versions. Yeah.
Yeah. So what I do is, I mean, I think the BV-BFV crowd does something. They sort of keep around all possible boundary conditions or something like that, or they're agnostic about boundary conditions. And I just say, you know what, it's a headache. I want to be in the BV world. So I just take the shortest path to staying in the BV world, which is to just impose a boundary condition. A boundary condition. But I think there's still a lot of very interesting stuff that you find once you do this. So the main theorem of my dissertation is that if you make this definition of quantum bulk boundary system, you have a factorization algebra of quantum observables for T. And it's a factorization algebra. Actually, this is probably requires a bit more work, but it's expected to be a BD0, Balin-Sindrinfeld factorization algebra, which means it's sort of lives in a sort of the quantum equivalent of shifted Poisson algebras. And let's see if I needed to say anything else. No. Okay, so let me make one or two more comments here. So let's see. So for free quantum bulk boundary systems, the constructions are much simpler, very beautiful, I would say. To toot my own horn. But this is work with joint work with Owen William and Brian Williams, and this is the archive reference. And I also want to get back to this point that I would like to say that this is a sort of program for the study of quantization of Poisson BV theories. So this is, again, following up on the intuition of Kontsevich. So the philosophy here is that there's the Poisson BV world, and then there's the bulk boundary system world. So as an example, we have, for example, the theory, there's something called Poisson mechanics, Poisson topological mechanics. On R, and its universal bulk is the Poisson sigma model. On H. You have classical observables here, which is just corresponds to the algebra O of M, or let's say O of P, where P is a Poisson manifold. And over here, with the bulk boundary system has a factorization algebra, also of classical observables. And you find that when you push forward this factorization algebra along the projection to the boundary here, that you get a factorization algebra on this boundary, which is equivalent to the classical observables of the Poisson topological mechanics. So the philosophy is that to obtain the quantum observables, so Kontsevich sort of did this, it's the functions on P again with the star product, and conjecturally one way to interpret how he did this is that this isn't quite proven. I'd like to prove this, but that you take the quantum observables for the Poisson sigma model, take the quantum observables and you push those forward. So my sort of argument is that basically Kontsevich produced this star product by quantizing this bulk boundary system and then using this quantization of the bulk boundary system to induce a quantization of the boundary object. And that's sort of the general approach you might want to take to quantizing Poisson BV theories, is to quantize the universal bulk boundary system and then push forward back to the boundary. All right, so let me now talk about the specific examples I had in mind. So this is a good place. This is a fresh refresh. So it's a good place to, yes, if you've lost the train of thought up to now is a good place to tune back in. So anyway, like I said, a symplectic vector space and a Lagrangian subspace determine a bulk boundary system on the non-negative half line with this space of fields, the Durand complex with values in V. The boundary fields are just V, and the boundary condition is the Lagrangian subspace that we started with. And as a beginning proposition, we have an equivalence of factorization algebras on R, where this is the factorization algebra associated to the algebra of functions on V. This is the algebra of polynomial functions on V, and this is the algebra of polynomial functions on L. And the pullback of functions along the inclusion here induces the module structure for this object. So that's sort of that's the sort of classical object that we will now quantize. So what do we expect when we quantize? Well, let me introduce some notation. So it's again going to be a factorization algebra associated to an algebra and a module. So let me tell you what the algebra is. Well, it's the Weil algebra on V. Just to say, it's the tensor algebra on V dual modulo the two-sided ideal generated by relations of this form. And then we have also a Fock module, which has a right, it's a right module for the Weil algebra, which is the Weil algebra modulo this right ideal generated by the linear functions on V which vanish on L. And the result here is that there's an equivalence of factorization algebras between the quantum observables for the topological mechanics and the factorization algebra W of V corresponding to this algebra in this module. So these are the sorts of objects you expect upon quantization. So that's the cool thing. We reproduce not only the algebra of observables, but also a module for that algebra by choosing this boundary condition. All right, so classical BV theory, classical BF theory is another similar example. It's essentially topological mechanics, but this sort of more stacky target. So instead of just some symplectic vector space, we take the cotangent bundle of the space BG. And that's the target of this particular topological mechanics. And for the Lagrangian, we're going to take the cotangent fiber as the Lagrangian. And structurally, for people that are sufficiently homotopical, well, it should not be any different from topological mechanics, but unfortunately, we have, when we do field theory, there's this sort of artificial distinction between free and interacting ones, and BF theory is an interacting theory. So we have to actually use the full machinery of interacting theories. And so at the classical level, that's all right. That's not too hard. And we can show that basically we get the factorization algebra, which is associated to this particular algebra and this particular module of this algebra. So that's what happens at the classical level. And then now what do we expect at the quantum level? So what sort of algebra and module do we expect to get upon quantization? So one way to go about this is to ask, well, this is sim of G shifted by 1. It's not just a commutative algebra. It in fact also has a P0 structure. And on linear generators, it's just induced from the Lie algebra bracket. And one natural quantization of this is this BD algebra of Chevalier-Eilenberg chains on G.
So Eugene, I
Yes.
just wanted to remind you of the time.
5 minutes. Okay, thank you. All right. So on the boundary, we get this natural BD0. We'll expect this cochain complex. And now what about the algebra? So as a graded algebra, we sort of should expect it to be a Weil algebra, sort of like for topological mechanics, where we have, it's generated by a copy of G in degree -1 and a copy of G in degree +1. And there's the natural Weil relations. And this object, whatever this object is, it has also a differential on it. And this was described by Kosten and Sternberg. So when G is unimodular, that complex, as a complex, is isomorphic to the Chevalier-Eilenberg cochains of G with values in the chains of G. But you can't, the algebra structure is a little bit more subtle. Anyway, so this object in the bulk and this object on the boundary is what we expect. So now we ask, when we quantize using the Costello-Guilliam type techniques, what happens? So what I found was that for unimodular G, the observables associated to the full space is the expected boundary observables. And as a cochain complex, the observables associated to the the positive reals is what you would expect for the bulk observables. So this isn't, this is consistent, but isn't the full proof. It's consistent with the expectation that the quantum observables will be equivalent to the factorization algebra associated to the algebra G, C star G with values in C star G, and the module C star G. So it's consistent with the expectation, but it's not the full proof. In particular, I don't examine the multiplication structure in here or the action of this object on this object. So that's incomplete work, but it's still exciting because it's very difficult to compute observables for interacting theories. So it was a completely explicit computation. And I just want to make a quick note is if we don't have a unimodular Lie algebra, well, we have to replace the chains with some twisted version, which is determined by the trace in the adjoint representation, which is an element of the one cochains of G. And then other comment is, again, the theorem has not determined the algebra structure induced on this object from the factorization algebra. All right, so I don't have time to explain BF theory, but I would like to study BF theory in higher dimensions and reproduce what is known as the EN enveloping algebra for G, which is the higher analog of the chains on G, which is what we had on the boundary in 1 dimensions. So this is my conjecture. Be nice to show this, that's work in progress. So let me very quickly summarize. So we surveyed some recently developed general techniques for studying quantization of bulk boundary system and Poisson BV theories. In some circumstances, there were already quantization Ansätze for these objects. For example, the Weil algebra or the chains on G. And we described some results which show that the general techniques match with the specific Ansätze. So the next question might be, well, look towards the future and see if the general techniques can apply in situations that weren't already studied before. For example, theories of a mixed topological and holomorphic nature. Okay, I'll stop there. Thank you very much for listening.
Thank you very much for the great talk, Eugene. So, yeah, let's dive into questions. Nicola is saying, can you go back to the conjecture?
Yes, thank you. Yeah.
Do you have questions, Nicola? You should raise your hand if you have questions. Okay, so he doesn't have any question. He just wanted to see the conjecture. But we have a question from Pelé.
Yes.
Hey, how's it going?
Good. And you?
Yeah, I'm fine. Thank you. That was a great talk. And also thank you for teaching me the plural of the word Ansatz. I had no
Is
idea.
that the right plural?
Sorry?
German?
I have no idea. I'm not German. I don't know. I mean,
Nima, is that the right plural?
Ansätze, yes.
Ansätze.
Yes.
wow. Lucas confirms. Like, well, I think he's a little bit more German than you, Nima, so I'm gonna go with his.
Oh, what the hell? I can only.
Sorry. Okay. So yeah. So question. Okay. I don't know. Maybe this is more appropriate for the discussion afterwards. But anyway. So in the Costello-Guilliam picture, so these field theories. So like in a BV field theory, you always require like a complex of L-infinity algebras or DG Lie algebras, for which like the differentials are elliptic differential operators on the manifold on the closest.
Yes.
And if you have a boundary, right, there's, I guess, like you can have another vector bundle on the boundary, and then maybe you have like another sort of condition that the differential sort of maps some field on the bulk to a field into the boundary. But sort of there are general conditions for sort of a whole system like this to be an elliptic linear differential operator.
Yes.
So my question is, which is sort of essentially what guarantees that there are parametrices for such systems. So does your work essentially work for all such what I think are called coercive or elliptic boundary conditions?
I thought about, I wanted to find, maybe you can give me some sources, but I searched for a while to find the sort of results that I wanted about general.
I think the Book of Hormander is always like the sort of canonical text.
By Malraux, you said?
So there's these epic tomes of Lars Hormander, which he wrote in the 60s or until 80s, and they're all about linear partial differential equations.
Yeah, again, I wasn't quite able to find the results I wanted there, but maybe you could help me interpret. But anyway, the theories I consider are of a particular form, so that the verification is not very difficult.
So I think in your work you have some like a bundle on the boundary, which is half the dimension of half the rank of the bundle in the bulk.
Yes.
Something like this. Like that is always such a boundary condition, but there are more. So I thought like maybe.
Yeah. No. It would be nice to apply to more general situations as well. I just cut down the problem a little bit so that it would, so that I didn't have to dig through a lot of PDEs.
Wade through endless technicalities.
Yeah.
Okay. So, thank you.
All right. So any other questions? Okay, we have another question from Luke. Please.
Yeah. Something very simple. So for the topological mechanics example, can you do the same for fermions as well? So where you get like your Fock space is a isometric thing?
That's a good question. I think you can definitely do basically the same example, but have it be in odd degree. And then you need actually, instead of a symplectic structure, like a bilinear symmetric pairing on V. And then, yes, it's a similar construction. But I'm not, it's a very good question. I don't know why I haven't actually fully worked it out before, but.
Oh, it's not written down.
No, it's not actually written down, but I think it'll be I think it's basically the exact same proof.
Okay, cool.
Yeah.
All right. So any other questions? All right. So if not, then let's thank Eugene again for the great talk. Thanks. And so, yeah, I just say a couple of words.